So this is a continuation of our analysis on the stages of behavior of beams. So in our first example, what we did is just to determine whether the beam is cracked or not. And you will notice that in the example, we use the gross concrete area to solve for the property Ig and C. Okay, so here in the example, the next lecture on the Uncracked stage, we are going to use the reinforced concrete section considering both the concrete and the steel as a material. And if you will notice, the first thing we have to do is to transform your reinforced concrete section to what you call a transformed section. So your AS now will be converted into an equivalent concrete section, which are shown here as the shaded area. And the transformation factor that we are going to use is n minus 1. We know that steel is n times as hard as concrete, and you call that n the modular ratio. But why is it that there is a negative 1 dev? The reason for that is because here your net concrete section is simply equal to your gross minus your steel area. So your area here will now be simply equal to the concrete plus the transformed steel section, or simply A steel transformed. Okay, so your area of steel transformed is now equivalent to n times the area of steel. And if we are going to substitute AC equal to AG minus AS plus this one, your transformed area now becomes AG plus N minus 1 AS. Okay, so this is now your AG, and this is now your N minus 1 AS. Okay, so since we are still on the elastic side, remember what I told you. The strain diagram is still following the strain compatibility assumption, and also the stress diagram is still on the linear behavior, linear elastic behavior. So how are we going to compute the properties of the section? So first, we define what is your modular ratio by simply dividing ES and EC. Normally, this is rounded to the next higher integer. And the location of the neutral axis can actually be determined by simply using the Varignon's theorem, which states that the area multiplied by the centroidal distance is simply equal to the summation of individual small areas multiplied by their corresponding distance from their centroids. Or simply, summation AY at the top is equal to summation of AY at the bottom. So you can use this or this as your reference equation or formula. Okay, let's now derive the formula for KD. Okay, KD is actually a variable used to describe the distance from the top fiber, okay, top or the compression fiber to the neutral axis, okay? Always the reference is on the top or simply the compression fiber. If the steel is at the bottom, then the compression fiber is at the top. Always take note that steel is at the tension side while the other side must be in compression. So using this principle to solve for your KD, we take note of the first formula that A KD, so this is now your Y bar, is equal to summation of AY, and this is simply equal to A1 Y1 plus A2 Y2, where A1 and Y1, A2 and Y2 are simply this area. Okay, so area here, A1 is simply the area of the rectangle, and A2 is simply the area of the transformed section. Okay, so this is the area gross, and this is the area of the transformed steel section. Okay, so you see the two rectangles drawn on either side. Okay, so we know that area total, this is the area total, is simply BH. Okay, so A1 here is BH, and A2 is n minus 1 of AS. So the total area will simply the sum of the two individual areas. This is A1 and A2. Okay. And if we are going to solve for Y1, okay, so where is your Y1? Y1 is from the centroid to the top, so this is H over 2, okay, and this is from the centroid to the top, this is the distance of the steel bar. We'll look at the figure on top. Okay, so from the steel bar up to there, you have a D distance. Okay, such that if I substitute it here, I will now get BH plus n minus 1 ASKD is equal to BH times H over 2 plus n minus 1 AS times T. Okay, so your KD now can be solved by arranging. Okay, you put this at the bottom and then put this as your numerator. For the moment of inertia, the neutral axis, okay, so it's now longer, okay, not IG, okay, so this is wrong. We're not going to use the cross section. We are going to use the I and A. So the I and A is simply the sum of both the concrete and the transformed steel. And we must use the transformed or transfer formula for moment of inertia in this particular point, such that your transfer formula is simply equal to I and A is summation of IG plus AD squared, or AX. Let's choose X. Okay. Okay, so where's your IG now? Your IG is the individual IGs of the areas. Okay, so we have only two area. The first area is BH. So what's the IG of that area? So it's a BH cube over 12. This is for your concrete. And your AX squared is simply BH A, and X is this one. Okay, so this is your A1 X1 squared. And this is your IG1. Okay, so for your IG2 is 0. There's no moment of inertia for steel section except for the AX squared part. So this is now your A2 and then X2 squared. Okay, so this formula is only good for, remember that this is only good for rectangular sections. Okay, next we solve the stresses by using the flexural stress formula. So your FCC is MC over I, but this case your C is KD and your IG is INA. Okay, so we have to compare this to the allowable stress for WSD, and FCT is compared to your FR, allowable flexural tensile stress, because this is in compression and this is in tension. For the steel level, Fs over N is Md minus Kd over In. So take a look that Fs here has an N here because we are converting it back to concrete. Okay, so we have to divide it by N. And it must be compared to your allowable tension steel stress. So this is tension. Allowed. Okay, still in the WSD format. Okay. So for the crack stage, what will happen is that the concrete area below the neutral axis will be neglected, okay? Because it has already cracked. It will be void and neglected. That's why your crack stage transformed section will will be something like this. Okay, it's like a floating steel section here, converted steel section. Okay, so for this, the formula we're going to use is Varignon's formula number 2. Which states that AY top is equal to AY at the bottom. Okay, so this is at the top and this is the bottom. So what's your area at the top? It's BKD. What's the distance to the centroid there? It's 1/2 of KD there. And this is NAS. Oh, remember there's no longer -1 there because there's no concrete here. So NAS times, okay, if this is your D, this must be D minus KD. Okay? So if you manipulate this by doing algebra, so we will arrive with a quadratic formula to solve for KD. Okay? So this is a BKD squared over 2 is equal to NASD minus NASKD. Okay, this one you distribute it there. And then KD squared, you divide it by B. You put 2 on top, so 2 NASD, and so on. Okay, so the KD squared now becomes plus 2 NASKD over B minus 2 NASD over B is equal to 0. Then solve quadratic formula. You can get the answer for KD. Okay, for the equilibrium of internal forces condition, we're now going to get the value of your C and T on the basis of this figure here. Okay, so let's look at that figure and solve for C. Okay, let's draw it here again. Okay, so this is now your figure. So this is now your C. This is your T. So we know that this is FC. And this is again, what's this? This KD. Okay. And then we have here AD. Okay, so C is simply the area of this rectangle here. 1/2 FC KDB. And T is simply equal to the steel area. We have a steel area there, AS, multiplied by the stress. The stress here is equivalent to Fs. So we know that that force is equal to the area times the stress. So this is a simple area there. Okay? And the moment is simply this couple because equilibrium of forces makes C equals to T. You call this now a couple. A couple are two forces which are equal in magnitude but opposite in direction. So you will constitute a moment here equivalent to MC, which is CJD. Okay, so what is JD? JD is this one here, where JD is simply equal to D minus 1/3. This is 1/3 of KD. Okay, so D minus KD over 3. So this is now MC is CJD, C times JD, and MS is T times JD. So you just substitute C there and substitute JD there, you get these two equations here. Take note that JD is D minus KD over 3, or J is simply 1 minus K over 3. Okay, so that's how you solve for the equilibrium condition on the internal forces. So for the crack analysis, in WST, the following formula may be used to determine the crack moment of inertia, ICR, applicable for rectangular sections only. So this is a shortcut formula I'm going to give, but take note that this is only good for crack section, no? Crack rectangular section. Okay, so on the next video, I will be discussing working stress design procedure. For now, I'd like you to understand the concept of how to determine the properties of the section, the elastic section, using the transform section method.